here's our agenda for today, a brief intro to graph databases and Neo4j, and then we're going to dive into some natural language processing tasks, specifically how we can represent text as a graph. We'll get into mining word associations from a text corpus, and then look at some techniques for graph-based summarization. And finally, we'll have a demo with content recommendations. So we can really think of this talk as sort of a survey of various natural language processing methods using graphs. Okay, so intro to graph databases in Neo4j. So just so that we're all on the same page here, we're going to be talking about graphs quite a bit. So these are charts, and this is a graph. So when we say graph, we're talking about some data structure with nodes and relationships that connect those nodes. We're not talking about things like pie charts and line charts. Okay, so if we know what graphs are, what's a graph database? Well, simply thinking, a graph database is a database that stores graphs. Neo4j is a type of graph database. There's a bit more to it than that. There are sort of three key elements that we think about when we talk about a graph database. The first is the property graph data model. We'll look at this in a bit more detail in a minute here. Also, native graph processing, so the ability to traverse our graph very, very efficiently. And then some query language, some query construct to be able to do that. And with Neo4j, we use the Cypher query language. So let's look at those in a bit more detail, starting with the property graph model. So one thing that I think is really great and really intuitive about dealing with graphs is that when we go to model a problem, often we go to the whiteboard and we draw out the domain of the problem we're modeling. And what we end up drawing is a graph, something like this. So if we wanted to represent some organization hierarchy, it might look something like this. And this is a graph. We have nodes, we have relationships connecting those nodes. And the great thing about a graph database is then when we go to model this data set in a graph database, the data model is exactly the same as the whiteboard model that we drew out. So we don't have any mismatch between the way we model the data and the way we think about it in the real world. Compare this to the relational model. So here on the right, we have the graph model where we have a simple social network. Andreas, he knows 3 people. That's very natural to represent in the graph model. If we're representing this in a relational model, we need a join table to be able to represent these relationships. And this might work out okay for sort of one-hop relationships, but imagine if we had a much more complex graph. This becomes very complicated and performance breaks down very quickly. Let's look at the property graph in a bit more detail. So the nodes, these are the objects in our graph. We can have name value properties on these nodes. So we have a person node, that's the label for the node, with the name value pairs name Dan, the date that he was born, his Twitter handle. Similarly, we have relationships that connect these nodes that can also have name value pairs and also have a type. So we have a relationship between Dan and the car that he drives with the date that he's driven it. So this is our property graph model. So we need some way to interact with our graph model, and we do this using Cypher, the graph query language. Cypher is all about pattern matching. So we're representing labels and properties. Properties are within curly braces. We're defining nodes within parentheses and relationships within brackets. So if we were to execute this query, we would create 2 nodes in our graph, one for Dan, one for Anne, with a loves relationship connecting them. And we'll see a lot more Cypher as we dive into some examples. Okay, so that was our brief intro to Neo4j. I'm sure that was a brief review for some of you. So let's dive into the natural language processing stuff now. So let's see what exactly do we mean when we say natural language processing with graphs. Well, let's break this down. Natural language processing is all about uncovering some meaning from text and with graphs. So we're going to be using the graph data model that we looked at previously, the property graph model. So we're going to be uncovering meaning from text using this property graph model. And the examples we'll use Neo4j and Cypher. So the first thing we need to do is represent our text as a graph. Traditionally, using sort of standard methods of natural language processing, instead of a graph, we would build a vector model, like a vector space model, something like that. But we're not going to do that. We're going to build the text adjacency graph. So we're going to have word nodes with a relationship between them when we've seen those words together in our text corpus. So here's an example. If we had the phrase, "my cat eats," we would have 3 nodes in our graph, one for each word. And we're storing the words as properties on those nodes. And we would have the word pairs that we've seen connected by a next relationship. So we have my cats with a next relationship, and we have cat eats with a next relationship. So this is the sort of the basic model that we're going to use for all of our examples with natural language processing. So if we have the sentence, "my cat eats fish on Saturday," how can we build our text adjacency graph with this? Well, this is what we want to end up with. A node for each word with these next relationships connecting them. How can we do that in Cypher? Well, we can do something like this. So what is this doing? Let's dive in here. So in this first line, we're taking in our sentence. We're lowercasing everything. You can also filter out stop words, punctuation, things like that. But for simplicity here, we're just converting everything to lowercase. And then we're splitting that into an array of words. And we're piping that through to the next line using the with statement. We're then going to iterate with I as a counter variable through each element of our array here, our array of words. And we're going to use the merge statement. Merge is a get or create. So here we're starting with the first word in the array, so my, and we're doing a lookup. Does this node already exist? Is there a node with the property my for the name? If this doesn't exist, we create it. We do that for the next word in the array, so cat. And then finally, we create this next relationship between those 2 words. And so if we were to run this Cypher statement, we would end up with the graph on the bottom of the screen. That's our basic text adjacency graph. So that's how we represent one sentence, but we want to represent an entire text corpus, right? So many, many sentences. So how can we do that? Well, we can do that with the same Cypher query again. So now our sentence is, "his dog eats turkey on Thursday." The graph at the bottom is what we want to end up with. So notice that eats appears in the previous sentence and in this sentence now. So we don't want to create a new node for that. Instead, using the merge command, we'll make sure that we're creating relationships to the already existing eats node in our graph. So if we run this query again, this time using our new sentence, you can see the graph that we'll end up with. And if we had a large corpus, we would do this over and over again, building up our text adjacency graph. And now this model isn't quite complete for all the examples that we want to accomplish here. One thing that we can do is add what I'll call the fellowship frequency. This is the number of times that we've seen a given word pair in the corpus. And what we'll do is we'll add a counter on the relationship. So we'll increment that each time that we see the that word pair. And I just had a question about what the keyword unwind is doing in our example. So if we look at this here, basically what unwind is doing is it's allowing us to iterate over the previous array. And we're passing unwind the range function. So it basically allows us to iterate with a counter variable. So I takes on the value 0, and that allows us to access the first element in the array, and then create that adjacency graph. And we're specifying the size of the array -2 because we want to start at the 0th element, which is the first in the array, and then we're looking at the next element, so we only need to go up to the size of the array -2. Okay, so we were talking about adding our word pair count. Right, so we're doing this. So now we're storing in a property on the relationship a count for the number of times that we've seen those word pairs in our text corpus. And one other thing that we want to keep track of are individual word counts. So each time we've seen the word, we're also going to store a counter on the node to keep track of the number of times we've seen that specific word. And this will allow us to do things like query for the most common word. So what are the most common words in our corpus? With these two sentences, it's eats. We can also do things that are a bit more interesting, like look at word pair frequencies or co-locations, words that are co-located together. So this example is from a product review corpus. What are the most common word pairs that are appearing? So we have this TV, TV4, great picture. So this is from an example that we'll see later in a minute here. Okay, great. So that is our basic text adjacency graph. We're going to be using that data model as we go through some natural language processing tasks. And the first task that we're going to look at is mining word associations. So what do we mean by that? Well, there are two basic types of word associations in natural language processing: paradigmatic and syntagmatic. Paradigmatic can be thought of as words that could be substituted for each other. So think of Monday, Thursday, cat, dog. We can substitute either of these in a sentence, and the sentence still probably makes sense. This is a useful first step for things like part of speech tagging. The other type of word association is syntagmatic. These are words that can be combined with each other, words that we often see together: cold weather, basically co-locations, things like that. We're just going to be talking about paradigmatic similarity. So what is the process for computing paradigmatic similarity in a text corpus? Well, the first thing we need to do is represent each word by its context. We then need to compute the context similarity, and then finally query for words that have this high similarity. Words above some threshold, we'll say they likely have a paradigmatic relation. So let's look at how we can do this using Cypher. So the first step, represent each word by its context. What does this mean? Well, taking our two sentences that we had before, basically by its context, what we mean are the words that it often appears with. So we're going to define a couple of functions here, right one and left one. Right one, we'll say this is some function that's going to retrieve every word that appears to the right of a given word. And we're going to have that return some set, so some set of words. Similarly, we'll define a left one function. So these are the set of words that appear in the text corpus exactly one spot to the left of this word. So when we say a context, This is what we're talking about, the words that, that it appears with. And of course, in a real world model, we would define right to and left to, and we would go at it in a bit more complicated manner, but just for simplicity, we're just going to define these two context functions. So looking at our graph here, let's see how we can do this in Cypher. And it ends up being pretty easy with just a simple a match statement here. So for left one, we match on the word that we're interested in, so cat, and then we define the pattern for identifying any word that appears to the left of cat, and then we return those words. And similarly for the for right one, we just basically reverse the pattern that we're defining. So these two Cypher functions will return a set of words that allow us to define the context for a given word. Okay, so that was step one. So in step two, we need to compute the similarity of these contexts. So how can we do that? Well, we can use what's called Jacquard similarity. So anytime you need to compare two sets, this is a great way to do that. We basically take the count of the intersection of the two sets and divide that by the size of the union of the two sets, and that number is our similarity. So that will range from 0 to 1. 0 if they have no words in common, 1 if the two sets are equal. And we can do that in Cypher. I'm not going to go through that query there, but there is a link at the bottom that sort of goes into detail with an example here. But basically what we're going to do is for every word pair that we have in our text corpus and our text adjacency graph, we're going to compute their context. We're going to compute the similarity of the context. And then because this is a graph, it's very easy to evolve our data model. So we're going to now create this related to relationship between words that have some context similarity, and we're going to store the coefficient of that similarity as a property on the relationship. So we've evolved our model a little bit. So here we see between the words opinion and idea, we have some concept of related to, and we have some similarity score for those two words. So now that we've done that, we can query our graph easily to find words that have high paradigmatic similarity. So this query is just looking for all of our word pairs that have some related to relationship, return those word pairs and order them by the similarity coefficient descending. So the highest similarity word pairs are at the top here. And so we have opinion, idea, students, college, students, people, important, hard. These are, from the text corpus we were looking at, these are the most similar words using our methodology. And this text corpus is from a series of college entrance essays, I think, which sort of explains the words we're seeing here. So looking at this, aside from some of the stop words like a and the, I think this largely makes sense. If you're interested in a more complete example of this, all of the code is on GitHub for this. Actually, in that first GitHub repository, there are 3 or 4 IPython notebooks that have all of the code for all the examples we're going through today. If you're interested in the concepts of word similarity, there's a great Coursera course on text analytics that some of these ideas are drawn from. And then finally, that last link is sort of a walkthrough of the example we just went through in a bit more detail. Great, so let's move on to our next task, which is graph-based summarization and keyword extraction. So what do we mean by this? Well, if we're given a text corpus, is there some way that we can summarize that corpus automatically, or some way that we can extract keywords tell us what this text corpus is about. And it turns out there's quite a bit of research into this area specific to graphs. We're going to look at a few of these in detail. The first one we'll look at, it comes from a paper called Text Rank, Bringing Order into Text. Basically, what this method involves is building the text adjacency graph that we used earlier, and then running PageRank on that graph. So PageRank is this iterative graph algorithm. Basically allows us to, for some graph, to identify the most important or most central nodes in the graph. So in the picture on the right there, the yellow node, he's the largest or the most important because of the size and number of the other nodes that point to him in the graph. This is sort of a very simple way to think about PageRank. Basically, for the text rank method, it's a bit more complex as a simplification of it, but basically what it's doing is running PageRank on our text adjacency graph and then taking the highest PageRank words and using those as candidates for keywords for the text. There's a Python implementation of this method as well as a link to the original paper, which I thought was interesting. So next, let's look at summarization and specifically opinion mining. So if we have, let's say, some corpus of product reviews for a specific product, we can look at the overall average of the rating, number of stars. We can look at a histogram of how those break down. That gives us some rough idea of how good this product is, what others think about it. But we want to be able to dive in a bit more deeper. We want to know what are the major complaints, what are the major compliments that people give about this. We want this in a concise and readable way, and we want to be able to do this automatically. This can help us get a lot more insight as a customer, but also as a business, understand what people think about our products. So that's the general area of opinion mining. Specifically from a graph-based approach, there's some great research on a method called OpenGnosis, which Kavita Ganasan, I'm probably mispronouncing that, so I apologize, but she has put a lot of work into this, and there have been some follow-on papers as well. And basically, the approach here is build a graph-based representation of the reviews, so very similar to the text adjacency graph that we built earlier. And then we identify and score some candidate summaries. Then we select the top summaries, the top candidates as our summary. So we already saw how to do number one. That's building our text adjacency graph. Let's look at how we can dive into that using some real-world data. So I put together a simple demo. Best Buy has a great API for retrieving product reviews. So the API basically takes a SKU or some identifier for a product and returns the user-submitted reviews for that product. So this should be familiar to us. This is our insert query from earlier. We're going to use this with the Best Buy API. In this example, we're also filtering out some stop words. So we're filtering out the, I, it, to, just to show you how we can do that. Other than that, it's pretty much the same as the example we were working with before. Here's a simple Python function that we're using to query the Best Buy API. We're looking at the first, I think, 500 reviews, and we're inserting those into our graph using that query we just saw. So that takes care of number one. Now we need some way to find and score our candidate summaries. So how do we do that? Well, basically, we're going to look for short paths in our graph up to about 5 words. And we're going to look for the word pairs that we've seen most frequently. So remember, we're keeping a counter on the next relationship, number of times that we've seen that relationship pair. So we're looking for short paths of about 5 words that have a very high number of counts. So we're summing the counts on the next relationship for the paths that we're looking at, and then we're normalizing by the number of nodes in that path to define some weight, and then we're returning the 10 candidate summaries, or the 10 paths, which end up being words, ranked by the weight. So let's look at some examples for some different products. So looking at Amazon Kindle and using this method, one of the top scoring phrases that comes out is easy to read in sunlight. So something a lot of users were talking about. Looking at some headphones, comfortable, great sound quality. For a Samsung washer, I love this washer. This was one of the candidates we came out. Being easy to use this vacuum for the Dyson. Bought this smart TV for the price for another Samsung TV. So using this approach works better for some products than others, but I think these all sort of make sense. And again, the code for this example is in that same GitHub repository that I linked to earlier in the form of an IPython notebook. Okay, so our last example that we're going to look at is in the area of content recommendation. So one thing that I think is really important is this idea of graphs providing structure of the conversation, and content mining gives us meaning. So if we can combine these two, so content mining with graphs, I think that can allow us to do some very powerful things. And one of those is content recommendation. So when we say recommendations, we're talking about recommending things to a user that they might be interested in. There are 2 basic approaches here. One is content-based filtering, where we're going to be recommending items to users based on what they've liked in the past. So if I like action movies and westerns, find more movies that are similar to those. The other method is collaborative filtering. So here, with collaborative filtering, we're making predictions based on finding similar users with similar tastes, looking at things that those users are interested in, and making recommendations based on that. For this example, we're just going to look at content-based filtering, so recommend items to people based on what they've liked in the past. And we're going to be looking at what I like to call the article graph. So we're going to be looking at articles from the internet that some user has shared or that they've read, that they've expressed some interest in. We're going to extract some keywords from those articles. We'll also keep track of the author of those articles as well. But this is the basic data model that we'll use to generate recommendations for other articles that the user might be interested in based on what they've read or shared previously. So how do we do this? Basically what I did was I looked at my read later list, so some articles that I had saved to read later. I extracted all the keywords from those using a Python library to do that automatically. And then I built up the graph. And then I went in and looked at New York Times, Google News, and some other sources just to pull down some other articles that I might possibly be interested in, and repeated the process. So extracted the keywords for those and inserted those in the graph. So let's look at an example here. So let's jump into Neo4j browser. And for those of you that haven't seen this before, this is the Neo4j browser. It's our web interface for interacting with Neo4j. So it allows us to see what we've stored in the graph, what node types we have, relationship types, the properties that we have. And then it also allows us to write some queries and execute those against Neo4j and visualize those in the browser. So let's look at an example here. Here's an example query. So we're going to match on this path for this user, so this is me, look at the articles that I've liked, and then we're going to traverse out from those articles to find the keywords of that article, and we're going to limit the results here, so we'll just look at, end up looking at one example with some of the keywords. So this is me, this is a user node, and this is a specific article that I've liked. It has the title, How California is Winning the Drought. So this is some article that I read. We're storing the URL so you can keep track of where that came from as a property on the node. And then this article has relationships to these keyword nodes. So we can see what this article is about. So from the title here, How California is Winning the Drought, let's see if these keywords make sense. We have California, irrigation, states, farmers. Okay, I think this makes sense, so that's good. So our first step for content recommendation is to figure out what are the keywords that I'm interested in. So this cipher query starts out similar to the previous query. So the pattern is find me in the graph, find the articles that I've liked, then find all of the keywords for those articles. But now we're just going to be looking at the text property of the keyword, and we're going to count the number of times that each keyword appears in the articles that I've liked, and we're going to return those in descending order. So we'll end up with keyword and the count. So these are the keywords that I'm most interested in. So algorithm, article, state, Neo4j, Montana. Okay, these seem to make sense. I used to live in Montana, by the way, so that's why that's in the list there. Okay, so now we can use that information to recommend articles that I might be interested in. So what does this query look like? Well, again, we see the same pattern here. Find me, find the articles that I like, find the keywords for these articles. But now we're going to go out from those keywords and we're going to find other articles that are about the same keywords. And we're filtering out any other articles that I've liked, because if I've liked it or if I've read it previously, that's not a valid recommendation. I don't need to be told I might be interested in something that I've already read. We're then going to, for each recommendation, we're just going to count the number of times that basically it has overlapping keywords with other articles that I'm interested in. And we're going to take the size of that, those overlapping keywords as the weight, and we're going to return 10 recommendations ordered by the weight in descending. So we'll end up with a list of prioritized recommendations of articles that I might be interested in reading. So let's see if this makes sense. So we have something about Donald Trump. Okay, something about the water in Flint, Michigan, something about economics. Yeah, so these seem to be sort of consistent with articles I might be interested in. So just glancing at that, yeah, I think that makes sense. Great, so that was our content recommendation example. All those queries are in the slides here. So you can check those out And again, all of the code for this example is in that same GitHub repository, also as a IPython notebook. Great, so let's just briefly look back at what we talked about here. So we had a brief intro to the property graph model. We saw how we can use the property graph model to represent text as a graph. And then we dove into some natural language processing tasks, mining word associations, opinion mining, and then a brief commendation example. I just want to leave you with some resources for further discovery. The first one is the Graph Databases O'Reilly book. This was updated last year to the second edition. This is just a great resource for learning more about graph use cases, specifically Neo4j, and this is available for free on graphdatabases.com. There are also a few articles and blogs specific to some of the things we talked about today, as well as some of the papers that I made reference to. And that is all I have prepared today. Hope you found that interesting. I think we might have time for some questions.
Excellent. Thank you so much, Will, and thank you everyone for already submitting so many great questions through the questions box. We'll go ahead and take a minute to correlate those questions. So continue to go ahead and submit those, and we'll be back with you in just a moment. All right, thank you so much. We will go ahead and start our live Q&A session now. So Will, our first question is, how do you treat or eliminate stop words?
Sure. So that's a great question. So stop words are simple, common words that don't really add any value. So things like at, is, the, things like that. And in the first example, I did not filter out stop words, but I think I show a simple example here of how we can do that. Yeah, okay. So in our opinion mining example, we took the query that we saw from the beginning on building our text adjacency graph. So we're using the with and the split to break our sentence into an array of words. And in the second line here, we're using with again. So you think of with as like a Unix pipe that sort of pipes the results into the next query. So we're using this with as kind of a filter here. And we're saying where So we're going over every word in our the result of our previous with statement here. So we have an array of words, and then we're using this where not W in, and then here we have some array of other words. So this is our array of stop words. So we have the, and, I, it, to, and we could make that something that's parameterized, something that's defined elsewhere that we're passing in to filter those out. So that's an example of how you can filter out stop words, because a lot of times those are not adding any extra meaning to your graph. So one way to do that is yeah, just like that in Cypher, using a simple filter.
All right, great. Our next question is, how can we extract the negative reviews? Since the positive reviews may have a large number, is it easy to extract it?
Yeah, that's an interesting question. You know, I'm not sure if it makes sense to filter out based on the rating. So one way to approach that would be to use the rating. So because these are our product reviews, we have some 1 to 5 star rating along with the text, and that's exposed in the Best Buy API as well. So we could pretty easily just filter on the rating. So only look at things below 3 stars. I'm not sure if that makes sense for sort of general opinion summarization. Maybe if we're only interested in finding the product defects, or if we're only interested in things that people thought were good or interesting about the product, we might want to look at only ratings above 3 stars. But I think in this example, that would be a good way to do it. That makes it easy because we have the rating. If we didn't have the rating, maybe we would have to do some sort of sentiment analysis to sort of establish if this is positive or negative, and then make a decision if we want to include that in our corpus, something like that.
All right, thank you. Next question. How would you avoid creating a filter bubble when doing new recommendations? That is, how do we recommend something new that could be of interest?
Sure. So yeah, this is a big problem in recommendations. Is sort of this idea that we're only being exposed to things that we've expressed interest in before. So if I'm on Netflix and I watch a bunch of Western movies, I'm only going to be recommended other Western movies. So this is a big problem in recommendations, and I think one of the answers is to use a combination of content-based filtering and collaborative filtering. So if we look at our overview slide here of different types of recommendations, the method we saw was content-based filtering, where we're using the keywords of articles to recommend similar articles. The other approach is to find similar users in our network and look at things that those users are interested in and make recommendations to us based on that. I think when we use collaborative filtering or a combination of those two approaches, oftentimes we're able to move beyond this filter bubble and beyond areas that we've only expressed interest in previously. So that would be my first approach, is implementing some hybrid collaborative content-based approach.
All right, great. Our next question is, do you have any pointers on using graphs for sentiment analysis?
Yeah, for sentiment analysis. Yeah, that's interesting. That's not something that that I have played around with, although I know there is a bit of research in the area. One approach that I've seen involved using a predefined dictionary of positive and negative words, and in your graph, adding a relationship that indicates if this word exists in the dictionary of positive, if it exists in the dictionary of negative words, and incorporating those relationships as you're traversing the graph. I know one of my coworkers put together an example for that. So when we when we send out the slides for this, we'll be sure to include a link to that as well. You can check that out.
All right, great. Thank you again for submitting all of your questions. We will take just a few more now, and we'll be back with you in just a moment. All right. As Neo4j is based off of Java, is it difficult to use in conjunction with Python? Specifically, was PyNeo2 used for all of these? If not, how is it done?
Yeah, okay, sure. So, yeah, so Neo4j is written in Java, and that's one way you can interact with Neo is using the Java API. However, all of these examples were done using Cypher, which is the Neo4j query language for graphs. And with Cypher and Neo4j's REST API, you can make requests to Neo4j server using a simple HTTP request. So it's not anything that is Java specific. Neo4j has a REST API. One of those endpoints takes a Cypher query and returns results based on that query. So these Python examples were done using Py2Neo, which is a great Python wrapper around the Neo4j REST API. But really, we could have done this in any language. There are great drivers in Ruby, JavaScript, Java, Scala, lots of other languages. So really, we could have used any. I like Python just because it's it's very readable, easy to distribute in the IPython notebook examples. But yeah, there's no reason that we were tied to anything Java related. The REST API and Cypher sort of take that dependency away.
All right, thank you so much. All right, that is all the time we have left for today. If you have any other questions, you can go ahead and submit those, and we